Shwmae, noswaith dda. Good evening. Shwmae is hello in Welsh, so I'm sure you can try Shwmae for me.
Let's try Shwmae.
Shwmae, that's it.
There we go. I've written the rest of the talk in Welsh, but as you've been so polite and introduced it in English, I will follow your lead. But
you've just won over the Welsh nation there with one word. One word. Well, welcome to you to the Argo Navis Follow the Stars conference. Croeso I gynhadledd Argo Navis, dilyn y sir. You are the last act. This is the final act of an incredible 2 days of speakers. Quite a challenge to organize, to put on, and to actually do it in the end. So we've really enjoyed these 2 days. Quite a few speakers, different topics, from astrotourism to astrophotography to space travel. We've had some weather people on. We always need them, don't we? As anybody wants to discover the night sky, you put most of your trust in your weather presenter, and therefore it's great to have you along. I've watched you on several television programs, Coronation Street, EastEnders, and of course my favourite Welsh program, Pobl y Cwm, which you had a cameo part in, didn't you? We just walked on in the back there with a telescope.
I didn't think anyone would recognise me with the giant hat, but it's nice that you did. So thank you.
So welcome to this wonderful, wonderful conference which we've held, organised by Menter, and we really appreciate the fact that it's been funded by some rural development plan program money from Europe, and they've managed to bring so many people together. It's really been a pick and mix of people, and we've really had a good time so far. So Chris, I know you're a professor, and you're aligned your work with Oxford University, and you're going to try and give us a fresh look. Really, this is the notes I've got. So you're probably going to be peeling for us tonight a fruit that gives us another insight into the universe which is around us and of which we are part of as well. And as somebody who does go out at night, I will be going out tonight if possible to see if I can see some stars and capture some images. But people like you certainly inspire. Okay, Chris Bach, it's over to you. The stage is yours, and I will step back quietly.
Thank you very much. It's nice to see the traditional Welsh gesture of a dragon's mouth being used as well. So that was great. And thank you very much for having me. Thank you all for spending some of your Tuesday evening with me. I'm always happy to talk to a bunch of people who are interested in looking at the night sky. I'm lucky enough to be a professional astronomer, to get paid, for helping students think hard about the universe these days. But I am at heart an amateur astronomer. I've still got my small 6-inch telescope out in the back garden, and I grew up in a local astronomical site and enjoying the dark skies of South Devon. Not quite as good as the ones you get in Wales, and perhaps not quite as good weather, for it's always sunny in Wales, I know. But somebody who grew up looking at the night sky and wondering about what it can tell us, because for me, the awe-inspiring thing of the science that we'll talk about tonight, and that lots of us spend our time thinking about, is that we can connect simple observations that we make by looking up at the night sky, or by imagining ourselves in other worlds, to some of the most cutting-edge science. Something that, with all due respect, my colleagues who work on quantum semiconductors or who work on condensed matter physics or any of these things don't have that privilege, whereas we can look as well as think. And really, I'll give you, because it's an evening talk and I know people will want to drift away quietly, though we've got time for questions, so start thinking of questions. And let me give you the punchline at the beginning, and it's this really, that astronomy has a reputation of being the preserve of the intelligent. And I think that's true, perhaps, of professional and amateur astronomers. If I tell somebody I'm an astronomer, they either ask whether I've met Brian Cox, the answer is yes, or they say, have you found aliens? The answer is probably not, or not yet if I'm feeling optimistic. Or they say something really odd. They say something like, oh, you must be very clever. It's genuinely one of the most common reactions. And I think what's happening is that there's this idea in the media that to do astrophysics, to do science, is to sit with equations and scribble, and to run down the street shouting Eureka after 20 years of work. And some people do that, but as an observational astronomer, as somebody who looks at the night sky, often the key scientific insight is to make a simple observation well. Tonight, in 3 different ways, is tell you about progress that we're making towards some of the obvious questions that we ask when we look up at the night sky. Things like, is there life out there? Where did it all come from? That sort of small question. But try and convince you that we can make some progress by making what are relatively straightforward observations, even if we sometimes do them in a complicated kind of way. Now, I hope you're now seeing my first slide. If that's not true, somebody interrupt me or put a message in the chat. I do have the chat open, by the way. So if you want to, we'll do questions at the end, but if you want to talk as we go, then do feel free to put a message there and I'll see it. So I'm talking about an observational astronomer. Being an observational astronomer, if it were clear in Oxford right now, I'd be looking at a view that was something like this. With Jupiter and Saturn, this is from a few weeks ago, apologies, so the moon's not there. I'd be looking at Jupiter and Saturn up in the night sky in the southeast. And they've been really rather beautiful the last few weeks. I particularly enjoyed the brilliance of Jupiter as the sun gets dark. Now, it's actually cloudy here tonight, but that's okay. Of course, we can take a closer look at Jupiter if we have telescopes, or if we take advantage of some of the wonders of the astrophotography that's done mostly by amateur astronomers. We can make a map of the clouds of Jupiter. Here is a recent version of a map of Jupiter. So just as you stretch the Earth out to form a rectangular map, we've done the same with Jupiter here. You can see there is the great red spot in the middle there. It's not looking hugely great or red at the minute. It's in one of its periodic phases of fading, but it's still a storm that's much larger than the Earth. There are the great belts and the south equatorial belt. You normally have 2 dark brown stripes that even I can see in my small telescope. One of them in the south around the great red spot has vanished at the minute. And we can sort of tell a story about what in this giant planet is happening. And I think it's just there's something wonderful about talking about weather on Jupiter. Of course, this is important science. Understanding planets like Jupiter helps us understand, for example, whether we've really got the right idea about the processes that are happening in our own atmosphere, which we care about for climate reasons, and of course, most importantly, for weather forecasting. So there is a scientific reason here, but actually, there's also just something fun. Richard Feynman complained about the idea that understanding that Jupiter was a big ball of gas took away the magic. He said, what men are poets if when Jupiter is a man, they sing, but when he is an immense ball of methane and ammonia gas, they stay silent. And I'm not going to attempt poetry, particularly for a Welsh audience, but I think there is poetry in this idea that we can look at Jupiter's weather and we can send a spacecraft to look at it. So these observations by mostly amateur astronomers using small telescopes here on Earth give us the big picture, and they're used to coordinate observations like this one. This is the glorious image returned on a recent pass by the Juno spacecraft, which is now just over 10 years since launch. And Juno does these long orbits, it swings just a few hundred kilometers above Jupiter's cloud tops. It takes these amazing pictures. Paul Johnson in the chat is asking about whether Jupiter's red spot, the storm which rotates, is slowing down. We're not really sure what's causing the changes in the red spot. We can talk more about that at the end if you remind me. But we've got these spacecraft out in the solar system. And I'm mentioning Juno in particular because Juno has taught us a really important lesson. This is a spacecraft that NASA selected to go to Jupiter. When this happens, a bunch of scientists get to argue about what scientific instruments get carried on board the spacecraft, which is now a precious thing because it's going, in the case of Juno, to somewhere that no spacecraft had been before. It's flying over the poles of Jupiter. And when they argued and fought about which instruments would produce the best science, they prioritized things like instruments that could measure the magnetic field. A lot of the mysteries of Jupiter's atmosphere are to do with how the planet's strong magnetic field interacts with particles from the sun, shapes the storms, causes the northern lights, the aurora borealis that we have here on Earth. And so they picked that sort of instruments, things sensitive particles and plasmas and magnetic fields, and they didn't pick a camera. And yet here I am showing you a picture from Juno. And what happened was a bunch of people, particularly the indefatigable Candy Hansen of Arizona, realized that this was ridiculous. You can't go to Jupiter and not take a camera. It's like going on holiday and not taking something to capture the occasional snap. And so they added a camera which was explicitly for the purpose of outreach and education. The idea was that it would take pictures like this so that I could show them to you, and the scientists could use them in their own presentations. But it turns out that when you go somewhere, the photos you take tell you a lot about the place. And even though we've got all of these highly sophisticated instruments on board Juno, measuring particles, measuring magnetic fields, helping us understand the aurora, helping us understand what's going on beneath the clouds, all of those observations need images to put them into context. And so this camera has proven to be incredibly useful. You can't go anywhere and not look. And sometimes just looking is the most valuable thing that you can do. Another example of a craft that's gone somewhere and looked is this thing. This is a photo from the Perseverance lander, NASA's latest Mars rover. And it's sort of, this is a panorama, so it's sort of a selfie, so it's stretched out. But you can see here that it's landed on Jezero crater, which we're pretty sure was an ancient lake bed. And you can sort of see that in the rocks. It looks like this was once a wet world. It's left these flattened rocks that you can see over in the right there. And the measurements that the spacecraft is making are confirming that this is indeed a place that was once covered in water. That's why it's exciting. We're there with Perseverance and with the other rovers to try and understand what is Mars, which was once a world of oceans and seas and rivers and perhaps rain, is now a dry desert, drier than dust. We want to understand that because it tells us something about how planets change and evolve, and it's about the possible fate of any Martian life that's on the surface there. Now, Perseverance has done a couple of things. It landed just over a year ago. This talk is well timed for anniversaries. And honestly, since it landed, a lot of the time it's been playing with the toys it brought with it. So Perseverance carried a little helicopter called Ingenuity. Ingenuity, hopefully you can see this moving, has been flying around the red planet, jumping up and then coming back down. It's done a couple of longer flights. It's now done 11 flights successfully. This is the first time that there's been powered flight in an atmosphere on a world other than the Earth. So this isn't a rocket, this is acting rather like a helicopter on Earth. And that's fun. But the idea of Ingenuity is to help Perseverance see. When you have a Mars rover like Perseverance, it probably costs something like $1 billion. It's actually a few billion, I think, for Perseverance. And so you want to be careful how you drive it. I'm actually just learning to drive, and I'm learning that you're careful if you drive a car down the street. If you've spent a couple of $1 billion on your car, you're really careful, especially if you're not behind the steering wheel. And so when the rover drivers in California at JPL send commands to Perseverance, they don't tell it to do anything risky. And in fact, it's programmed, if it gets to the point where it spots a rock it hasn't anticipated or it hasn't got specific instructions, it will stop. And this means the pace of exploration is really slow. So the longest lived rovers like Opportunity, which landed in 2003 and lasted for more than 15 years, covered about 26 miles, actually a little bit more than that, but less than 2 miles a year. Now that's slow going. Even if you're a distractible geologist, that's slow going. And so if you have a helicopter like Ingenuity, it could fly ahead of the rover, give you a perfect map and allow you to navigate and pick out your targets. So this is the first time this has been tried, but again, it's about helping us see a place differently. One of the reasons why you want Perseverance to get a move on is that it has a unique task. It's obviously there to analyze and understand the science of the place where it's landed, this ancient lake bed. But for all their ingenuity and technical capacity and engineering wow, rovers like this can't possibly do most of the experiments that we could do back on Earth. You can't fit a whole university geology lab onto a rover. You could do bits, but you can't do everything that you could do back here. So the ideal is to make a different kind of observation. You know, if you can't miniaturize your instruments, it's another simple idea, or you need to bring the rocks, the samples back to Earth. And Perseverance is the first step in doing that. It's just in the last few weeks. I know this doesn't look like a very good picture, but there, you can just see, this is a microscope, or rather a camera lens that's focusing. And you can see that this is a little sample tube that Perseverance has managed to fill with a little bit of Martian dust. And that tube will get left behind, and it will go on and it will make many more of these. And all over the floor of this crater, we're going to have carefully selected samples isolated in tubes. And this is part of a 10-year mission by both NASA and the European Space Agency, which we're part of here in the UK, to go and get these things and bring them back to Earth. So Perseverance is in the top left. We launch another lander that goes and lands in the middle there. It has a little European rover that will trundle off. It will collect, it's like some sort of really simple 1980s computer game. We'll collect up these tubes, put them back on the lander. That will then have a rocket, which will then launch. And will go back into Martian orbit. It will be met by another spacecraft, another European one, which will grab those samples and bring them back to Earth. So that in maybe the year 2031, maybe a little later than that, this piece of rock that was picked up by Perseverance will end up back in the laboratory. And some people, some lucky scientists will get to work with pristine Mars dust and try and understand what the red planet is really like. And I think it's it's the beginning of a remarkable experiment that we're embarked upon, trying to rescue and bring back these bits of Martian soil. Of course, the interest in Mars is partly because it's a planet, partly because it's different from the Earth, but also because it's a place where life, we think, could have existed. One of Perseverance's previous predecessors, previous rovers, Curiosity, went to a different lake bed, and it was designed to test out something that was called schnops, or to look for schnops, which are the elements that are needed, we think, for life. So carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. That's the raw ingredients that life uses to make its chemistry here on Earth. And so the idea is that if you have water, you have a temperate planet, and you have schnapps. So it always sounds to me like it's some sort of cocktail or something that an Austrian would give you to drink. But schnapps, then you have all the ingredients for life. And so by seeing whether Mars was inhabited, we can find out whether life would exist elsewhere in elsewhere in the galaxy. If life existed on both Mars and Earth, two worlds where there were the raw ingredients, then we can predict that life would be common in the cosmos. And the story of imagining life on Mars goes back a very long way, but we've learned recently, I think, that we need not confine ourselves to places where water used to exist on the surface. So we could think about the possibilities for life elsewhere in the solar system. So we can think about, for example, going back to Titan. So Titan is the largest moon of Saturn. It's the only moon in the solar system that has a thick atmosphere. It's got a thick nitrogen-rich atmosphere that has methane and other hydrocarbons in it. And so what that means is that it's often shrouded in an orange haze. so you can't see the surface. When the Voyager probes flew past in what the late 70s or early 80s, I think it was the very late 70s, they couldn't see through to the surface of Titan. Saturn's been visited since by the Cassini probe, the of the moons, and this is an image from Cassini tuned to a wavelength of light that allows it to see through the haze and to see the surface. And the dark patches that you're seeing on the surface here are lakes, but not of water. They're lakes of liquid methane. And if any of you learned about the water cycle at school, well, Titan has the equivalent, but it's not a water cycle. It's the methane cycle. So you have lakes of methane, they evaporate, particularly in the springtime. Methane goes up into the atmosphere, and then it falls as rain. Except that, and I think this would be useful here on Earth, because of the low gravity of Titan, the methane raindrops would be as large as tennis balls, but they fall slowly enough that you could dip around them as you were walking down the street. So if you've had experience living, as many of you do in Wales, of rain, you know you get soaked pretty quickly, particularly when it's coming horizontally at you, in my experience of walking in the Welsh mountains. On Titan, you'd be fine. You just have to stay awake, stay alert, and stay flexible, and you could dodge the methane rain as you wander around. But this combination of a methane cycle makes Titan a really fascinating place to think about life. And I don't think it's very likely that there's anything as complicated as a bacteria or a bacterium on Titan. But in those lakes, there may be patterns of repeated chemistry that are nearly life, that are like the conditions that existed in the very early Earth, back when the Earth's water oceans were first forming. Titan is an amazing place to think about going, and I'm really happy that we're going there. It's my friend Sarah Horst, who's a chemist who studies Titan and the worlds of the outer solar system. And this is an animation of a probe that she and many, many others are building called Dragonfly. And Dragonfly will launch in a few years' time, and a bit like Ingenuity, it's a little quadcopter. And this is what we think Titan looks like. This is a visualization of a real place on Titan. And the idea of the Dragonfly mission is that if you're only going to go once every 30 years or so to a world as interesting as Titan, you don't just want to stop in one place as the Mars rovers do. No, what you want to do instead is land, survey your surroundings, take some readings about the chemistry, understand what you're doing, recharge your batteries, and then take off. And a couple of weeks later, go to a different location. So I just think this is great fun. This is sort of an exploration mission. For the first time, we'll have a little robot hopping around the surface of another world. And I think that's really exciting. We can go beyond Titan. It's not just places with atmospheres that we've come to think about life. Take, for example, this world. This is Pluto, which was imaged by the New Horizons spacecraft, shown down there a few years ago. Now, Pluto turned out to be this amazingly interesting world when the New Horizons spacecraft flew past it. It turned out to have a surface that had lots of different areas. There's this sort of smooth heart-shaped region at the bottom here, and these darker regions, which are places where the ice on the surface has been processed by sunlight, really. But the point is that Pluto is a world where water is doing a lot of work to shape the surface. There are water ice mountains one could skid or ski or sledge on. I'm not quite sure at the temperature at which it would be, but certainly spectacular geological features. And certain features, like the smoothness of that heart-shaped region, which, because it shows no craters, may in fact be a young surface, one that's been turned over and processed recently. Certain features lead some scientists to believe that within Pluto, there is a water ocean, and underneath that, a rocky core. So this would be a place where we have water, where we have complex chemistry, where we have the schnapps, and where we have contact between water and the surface. It's not that dissimilar, particularly as Pluto seems to have an internal heat source of some sort, not that dissimilar to the places in the deep ocean where we think life got started on Earth. So maybe within this icy ball, there is an ocean with with living creatures. Now that's speculation, but there are many such ice worlds in the solar system. This is a picture of Europa. Actually, it's two pictures of Europa. So the main picture is, I think, an image from a spacecraft. I think it's actually from Galileo, which did for the Jupiter system what Cassini did for Saturn. Europa, I should have said, is one of the 4 big moons of Jupiter that was discovered by Galileo. And if you go out with a small telescope or even binoculars, or even for a tiny percentage of you, very sharp eyes, you can see Europa as one of the 4 Galilean moons around Jupiter in the sky this evening. But the background image, this sort of blue mottled pattern, that's a Hubble Space Telescope image of Europa. And if you can see in the bottom left, there's this little bright region. And that was there in January 2014 when this image was taken, and not since. And what that appears to be is a fountain of water bursting out from underneath the surface of Europa. So the many features on the surface, its relative craterlessness, these long streaks and cracks, which are reminiscent of what you might see on an ice flow, suggest that there is a water ocean underneath the surface of Europa. And we also think there's one under at least one of the other moons of Jupiter, Ganymede, and maybe Callisto as well, and even Saturn's moon Enceladus, which is no bigger really than the UK, has these fountains that the Cassini probe flew through. So these are all worlds in which water oceans exist. And if you ask a new discovery that we didn't know a little more than 10 years ago, but if you ask where the most common homes for life are in the solar system, the answer isn't on the surface of rocky planets like Earth and Mars, but rather the most common place where we may look for life is in the middle of an ice world like Europa and all the rest. We can, of course, keep going. We can keep expanding our definition of places that are friendly to life. You can insert your own joke about whichever place you want to laugh at in your locality here. It was only last year, in the middle of lockdown, I found myself wandering the deserted halls of Cardiff University with Professor Jane Greaves, who had been looking at Venus and had detected high up there's Jane and there is Venus, but she detected high up in the atmosphere of Venus the signature of what seems to be a molecule called phosphine. Now, this result has been disputed, but Jane and her team stand by it and they're looking for more data. But let's assume that they found phosphine. The reason this is exciting is that on Earth, phosphine is only found in places like this. It's a molecule that's basically created either in factories or in biology. And in particular, it's in penguin poo, contains phosphine. You can, in fact, detect penguins from orbit by looking for the phosphine. And so the suggestion is that if you see phosphine on Venus, high in the atmosphere of Venus, that might be a place where life is clinging on to a planet that really has no business being hospitable to life. The surface of Venus is hot, acidic, and under crushing pressure from a heavy runaway atmosphere. But high up in the atmosphere, there are regions where the temperature and the pressure are rather like Earth, but they're still acidic. So maybe this is some sort of bacteria that's clinging on and existing in very acidic conditions. Now, it's a hugely controversial idea, but it gives you an idea of how broad astronomers are now stretching the idea of a place in the universe where life could exist. Let's take that thought and do some observations with it. So having got the idea that life, or at least places for life to exist, might be common in the cosmos, we can look broadly around. This is a completely gratuitous picture of the night sky. You can see here there are stars, there's gas. Gas is great because from gas you can make more stars. And there's a dark lane on the left there, which is a place where dust, tiny particles no bigger than a sand grain, is blocking out the background light from the stars. And dust is great because from dust you make planets. And so we have all the raw ingredients for solar systems here. And we know that in our solar system, we've made a solar system that contains many homes for life. And the point about this is that I think how we look at these pictures should have changed completely in the last 10 years or so. How you think about things when you go outside and look up. Yes, Alan, it is indeed the North American Nebula in Cygnus. Good catch. When you go outside and look up, when you look at the night sky, when you look into the sky as I did as a kid and wonder what you're seeing there, you can now realize that what you're looking at is a map to a myriad population of worlds, to a place where planets exist. Because we now know, thanks to a whole series of observations that I can tell you about in the questions if you want, but we now know that planets in the universe are incredibly common, that most stars you could see with the naked eye, or in a picture like this, probably have planets going around them. And so I really think you should think of this as a map of worlds to consider. We've started trying to work out what kinds of planets are common, not in our solar system, but in the galaxy. And here's where we roughly are. So, yes, this is a graph. I'm sorry for showing you a graph halfway through a talk, but it's quite easy. Each dot is a planet. The higher up you are, the bigger the planet is. So Jupiter's are at the top, Neptune's are in the middle, Earth's are at the bottom. And then the longer you take to go around the sun, or your sun, the further to the right you are. And so you can see, for example, in the bottom left, we've got small worlds about the size of Earth, but they're very close to their star. Their year is just a day long. And so these are the lava worlds. They're probably rocky, but the rock will have melted. So there's no such thing as a solid surface. These would be volcanic and pretty hideous places to live. On the top left, we've got some of the first planets to be discovered. And these were a surprise. These are the hot Jupiters. These are planets as big as Jupiter, but they're hot. Astronomers, as well as making simple observations, I have to say, often make a hash of naming things, because the hot Jupiters are Jupiters that are hot. They're very close to their parent star. They go around the star in about a week, but they're gas giants. And that's weird, because in our solar system, the big planets, the Jupiters and the Saturns, well, they live out in the cold outer solar system. You have Mercury, Venus, Earth, Mars, then a gap for the asteroids, and then you have Jupiter and Saturn. Some of these worlds are so close to their parent star that they're evaporating. They're more like giant comets than planets at all. In between, we've got a common set of planets, ocean worlds and ice giants. So things like planets a little smaller than Neptune and Uranus. Those may be the most common planets of all. And beneath them, we're beginning to work out that rocky planets are common. And so as a comparative planetologist, this is amazing. I suddenly got a whole host of solar systems to compare and to help me understand how planets are forming. And actually, our understanding of how our solar system came to be is completely transformed by the knowledge that these other planets exist. We're beginning to realize that the formation of our solar system was a chaotic process, not one where things smoothly slotted into place, but perhaps where luck and chance played an enormous role. But to connect it to my previous story, we really care about homes for life, or you might care about homes for life. So people often talk about Earth-like planets, or sometimes people talk about planets which are not too hot and not too cold. In other words, planets which are in the Goldilocks zone, or sometimes called the habitable zone, the region around a star where a planet might have liquid water on its surface, say, so that it could support life. Well, we can actually be a bit more precise than this. I'm a big fan of a concept that's been popularized by Elizabeth Tasker, who's an astronomer at JAXA, at the Japanese Space Agency, and aided and vetted by various people on Twitter. Elizabeth came up with the Ecclewatts zone, which we decided was actually clearly the name of some ancient river god. But Ecclewatts stands for the region around a star where Earth could have liquid water on the surface. So if you took our Earth and our atmosphere and you plonked Earth at that point around a foreign star, would it still have liquid water on the surface? So this is quite a precise way of defining the number of Earth-like planets that might be friendly to life. And here's a confusing graph that you don't need to worry about. It's here to show you, mainly to remind me to tell you that a huge amount of work has gone into this, because you have to worry both about the planets that you've detected but also those that you haven't. And the upshot of all of this work is that about half of the sun-like stars in our galaxy have a rocky planet in the Ecclewatts zone. So that means there are something like 5 billion Earth-like planets in the Milky Way alone. You add on to that all of the ice worlds and the Titan-like worlds and maybe even the Venus-like worlds that exist in those solar systems. And we certainly live in a galaxy which has a few 100 billion stars, but at least 5, 10, 15, 20 billion homes for life. And that's one of the big revelations of astronomy in the last few years, is that we don't know if life is common. We don't know if life exists beyond us out in the solar system, but we do know that there are plenty of places where it might exist. Let's switch tack. I'm talking about the galaxy, so I should introduce you to it. Here is a beautiful map of the Milky Way. This is, in fact, a composite image from the European Space Agency's Gaia satellite. And this one image contains the light from 1.8 billion stars in a data release that Gaia put out earlier this year. And so you're seeing the light from about 1% of these here. And this is mapped onto the sky. So along the center here, you've got this band of light, which we call the Milky Way, which if you're in a dark sky site, you can see arcing overhead, particularly at this time of year. And then you can see these dust lanes. In the bottom right, you've got the two tiny satellite galaxies in the Milky Way. Well, I say tiny. They're called the Large and Small Magellanic Clouds. One of the revelations from Gaia, from this survey of the sky, is that the Large Magellanic Cloud is big. It may be as massive as the whole Milky Way within the volume in which it orbits. So our galaxy has this companion that's as significant, at least, as the moon is to the Earth. Now, Gaia does more than just make maps. Gaia also is beginning to tell us, because it looks with incredible, exquisite precision at the position of all of these stars, and because it's been looking for a while. So it tells us how these stars are moving. And so we can have some fun with that. So I've highlighted here that 40,000 nearest stars to the Earth, and we can now project the future 1.6 million years into the future. And so, I mean, there's not much to conclude from this other than that to realize that when we look at the night sky, it's not static. We're looking at a changing galaxy. But also, if we can do this, if we can project the stars further into the future, we can also project backwards, and we can look at how the galaxy has changed to produce the galaxy that we see today. And that's beginning to produce really interesting results. For example, I've already mentioned the Large and Small Magellanic Clouds, these dwarf galaxies, maybe not so dwarf-like, but these smaller galaxies that orbit the center of the Milky Way. Well, there've always been lots of these, but now we can trace the motions of their stars. We can see how they've affected the galaxy. And in particular, there's a galaxy which today is rather puny, called the Sagittarius Dwarf Galaxy. It's a dwarf galaxy whose stars mostly exist now in the direction of the Sagittarius spiral arm of the galaxy in the summer sky as we look at it from the UK. But this galaxy may have had a huge impact. The Milky Way. I'm hoping this will animate. What's happened is that this galaxy, over the last 6 to 7 billion years, has been captured by the Milky Way. No, that's the previous one. Come on. Why is this not playing? Oh, there we go. Sorry. Moving galaxies around takes a bit more effort than moving planets. Good. So what this animation will show is that this galaxy's had an effect on the Milky Way. So we're going to draw a graph as we go. So this line tells you about how many stars the Milky Way is forming. So when this line is low, the Milky Way is getting quieter. At this point, about 7 billion years ago, it's forming one star the size of the sun every year. Now that adds up over billions of years, but still. Watch what happens as the dwarf galaxy comes in. And about 6 billion years ago, it passes through the disk of our galaxy. We get this big peak in star formation. So our Milky Way suddenly forms a load of new stars because its gas and its dust is disrupted by the passage of this galaxy. But the galaxy's not done. It swings round, things quieten down again, and then 2 billion years ago, it comes close to the disk again, and we get another spike in star formation. And then a third one as it comes back round. So now we see the galaxy as these large loops. They're detected in the Gaia data, but we also, by looking carefully at the ages of stars, we also see this sort of pattern with peaks in the Milky Way's star formation history. So we're really beginning to understand our galaxy's history as really as a citizen of its cosmic neighborhood. And so the second thing I want to get across to you, yes, we've talked about life and planets, but we're also beginning to understand our galaxy better as well. Once you realize that our galaxy depends on the cosmic neighborhood, then it makes sense to have a look around. So one of my favorite projects of the last few years was done with this telescope. This is the Sloan Digital Sky Survey, which exists in New Mexico, a place where there are 320 clear nights a year. Sloan did a remarkable thing for 8 years. All it did was it stood there and it functioned as a giant camera. It allowed the sky to turn over the top of the camera, and it recorded the positions of billions of objects. And on the clearest nights, it went back to about 1 million of those objects, which have been identified as faint fuzzy blobs, the kind of things that might be galaxies. And it measured, on the clearest nights, it measured the distances to those galaxies. And so I can show you some of that data. I've got about half of them in this animation. And we'll start on the Milky Way. We're going to travel outwards through space. So you have to watch the credits first before we fly through the universe. But I want to emphasize this is real data. This is a visualization, yes, but it's visualization of real data with the real galaxies in the real places. It's not just an animation from some science fiction. So you see there's lots of spaces between the galaxies. Each one is a system of hundreds of billions of years, but they live more or less in isolation. We've seen they interact with their smaller neighbors occasionally. And when you get out about this far, a couple of billion years into the universe, billion light years into the universe, you can see there's this honeycomb structure. There are places where there are lots of galaxies, and there are places where there are very few galaxies. And that lumpiness of the universe appears to be a generic feature of our universe, that there really are these places where there are thousands, tens of thousands, maybe even hundreds of thousands of galaxies. And there are places where there are very few galaxies at all. You can see that more clearly in this still image from a similar survey called TDF. And there are a couple of things one would want to do with this lumpy universe. First of all, we want to explain it. And one of the ways we can explain it is that we think the universe started off very slightly lumpy. We see that in things like the cosmic microwave background, the earliest light that we receive from the universe. And gravity can work on tiny fluctuations, places which are maybe only 1/10,000th denser than their neighbors get more material because their gravity pulls more material in, and you exaggerate these differences. So we think we understand the physics, but that means that the lumpiness of the universe, how lumpy it is, tells us how much stuff there is in the universe. And this is a strong part of the evidence for one of the great mysteries of cosmology, the understanding of the universe as the whole. And really, the third and final idea I want to leave you with is that we are struggling to understand the universe as a whole. It should be the simplest questions of all. If I have to worry about life, I have to think about chemistry and biology and physics and planet formation and magnetic fields and all the rest of it. If I want to understand cosmology, how the universe as a whole is expanding, I should just be able to write down a few basic equations. And yet, we find that though we're sure that the universe is 13.8 billion years old or so, and that it started in a hot, dense state that for now we might as well call the Big Bang, and then expanded rapidly, we're struggling with such fundamental questions as what is the universe made of? Because observations like these, a simple observation of how lumpy the universe is, though one made with great expense and great effort and a lot of careful thinking, tells us that there's more stuff in the universe to account for with the number of stars and the amount of gas and the amount of dust and even the amount of planets that we can see. And so we believe that the universe is filled, that 6/7 of the stuff in the universe is in the form of what's called dark matter, material which has gravity, but which doesn't interact with light. Maybe made up of neutral particles, or it may be something more exotic, but we don't know what that is. So we don't know what most of the universe is made of. We can play a different game. Having observed how lumpy our local universe is, we can take pictures of the deep universe. This is one of the Hubble deep fields. So Sloan, you can think of as an experiment where the telescope stays still, the sky turns overhead, and it records images as it goes. In this case, we do the opposite. We point the telescope at one patch of sky and we wait for a very long time, allowing the faintest objects to be seen. And in this case, almost every dot you can see in this image isn't a star, but is in fact a distant galaxy. I think there are 4 stars in this image. I can see 3 of them now. And then everything else is a galaxy. So these are galaxies whose light has been traveling towards us for more than 10 billion years. So, which has been traveling towards us, in fact, for more than 3/4 of the age of the universe. And so what that means is they're telling us about what the universe was like that long ago. And what we can see is that, well, you can't see perhaps from the photo, but we can see that the stars in the galaxies are younger. That's good, because we think the universe was born in the Big Bang nearly 14 billion years ago. But also, the galaxies turn out to be much closer together. And we can measure how much closer together they are compared to what we see in the local universe in Sloan, and use that to measure how fast the universe has been expanding. And what we find is that the universe has been not only expanding for the last 14 billion years, but that for most of that time, especially the second half of it, it's actually been speeding up. So the expansion of the universe is accelerating. And that's puzzling, because we think that gravity should slow down the expansion. And so we have a sort of anti-gravity force that's pushing outwards, that's causing the universe's expansion to speed up. And we have no idea what that force is. We call it by the name dark energy, which I hate because I don't understand what it means for energy to be dark, but it's just a label for something we don't understand, which is that the expansion of the universe is speeding up. And so unlike in planets and in exoplanets, where we're making rapid progress and new observations are bringing new discoveries, here we have some fundamental questions about how the universe is behaving, where progress is difficult, but we hope help is on the way. Many of you will know about this thing. This is the James Webb Space Telescope with its magnificent 8-meter mirror, which is now on its way, if it's not there already, to French Guiana in South America, where it'll be loaded onto a European Ariane rocket and launched into space in December the 18th, in fact. Now, JWST has been long awaited. It's been delayed many, many times, but it is now nearly ready for launch. And everyone is excited because this is a machine that was built to do many things, including looking at some of the planets around other stars. But it's also a first light machine. It's sensitive to infrared light, which we get from the first galaxies and the first stars. And so we think that JWST may tell us phases of the universe's existence and give us new light on what happened right at the beginning, the first part of our cosmic story. It's going to completely, before it does that, it's going to completely ruin Christmas for me and lots of other astronomers, assuming it does launch in December the 18th. The mirror that you see here doesn't fit inside the rocket. It has to be folded up. And it takes about a month for it to unfurl and go from launch into working order. And if anything goes wrong in that month, the telescope will be a write-off and astronomy will be in crisis. So for a month, we're not going to do anything but check on the progress of JWST. There are no cameras on board. They've made the Juno mistake. And we're not going to watch the mirror unfurl. We're just going to have to wait for the computer on board to tell us that all is well, and then see the first images. Much less nerve-wracking, but I think as exciting as this thing. This is a telescope or an observatory being built in northern Chile. This is the housing for the Vera Rubin Observatory. And Rubin is a sort of super Sloan. It's an 8-meter telescope, as big as the biggest telescopes in the world today. But it's a survey telescope. It's been built to scan the sky roughly once every 3 nights. And it will produce not images, we'll do those too, but really you can think of it as producing a movie of the sky. So we will see asteroids zipping around, stars flickering, galaxies flickering as material falls into their black holes. We'll see Kuiper objects by Pluto. We will detect supernovae and gamma ray bursts and all sorts of things that go bang in the night. And I think with this window on the universe, giving us 30 terabytes of images a night and 10 million alerts to our mobile phones every evening, telling us that things have changed in the sky, we really will have a new window on the universe. And one of the purposes of the survey that the Vera Rubin Observatory will do is to shed light on the nature of dark energy and on what that pesky dark matter might be. So if I come back and talk to you on via Zoom or in person in 5 years' time, I'm sure I'll be able to tell you there are more planets. Maybe we'll have new ideas about ideas for life in the cosmos. We'll have new Gaia data and new maps of the Milky Way. I'm going to have to expand that middle section of the talk, but possibly we might make some progress on understanding what the universe is made of and why on earth it's expanding in the way it is. I can't answer those 2 questions right now, but I'll happily take any others. So thank you very much.
Thanks, Chris. There are a couple of questions that come up from Paul. Now, the first question is, are there any missions heading to Venus to analyze the atmosphere given the confliction views regarding phosphine?
Yeah, it's a good question. So there's been a lot of interest in Venus, not just because of the phosphine result, but because there was a general sense that Venus has mysteries that we don't understand, that it has potentially volcanoes on the surface. We don't really understand how it became the hellhole that it is. So there are 3 missions, 2 American and 1 European heading to Venus. They just got selected this year, but none of them will look directly for phosphine. To do that, we can do that with telescopes on the ground, and we're waiting for more telescope data from ALMA in particular, which is a telescope in Chile, but things have been delayed there because of the pandemic. There is a startup in New Zealand, Rocket Labs, that have said they'll send a probe to Venus for the scientists who found phosphine. And so there's an argument or discussion going on about what to send, and that would be a probe that goes into the atmosphere and measures on the way down. So that might happen in a couple of years' time, and that would be very exciting too.
Paul's also got a follow-up question here. Do you remember when Patrick Moore bet Brian May £1 to $1 million that alien life will not be found in the next 50 years?
Yeah, he did. I think Patrick was wise to realize that I think if aliens had been found, he'd be in good business. So I think he won either way on that one. I'm not sure what to bet. I don't know what I usually bet people a gin and tonic. So that's the currency. But I'm not sure how I would bet on whether we'd find life in the next 50 years. I think that the trouble is that unless something walks up and shakes your hand, understanding unequivocally what life is going to be really difficult. On Mars, Curiosity has found these little burps of methane, which could be bacteria under the surface, but might be geology, and they're difficult to find with other instruments. And just the argument about what's happening on Mars or Venus tells us how hard it's going to be to look at a planet around another star and work out whether there's life there. So I think it's tricky. I think the Martian samples are perhaps our best bet. But also, I talked about the fountains of water that are coming from Europa, where instead of, if you can fly a spacecraft through those, you can sample the ocean. So maybe that's a way we can directly test for life as well.
Well, there's one question I got actually. There is about the Vera Rubin Observatory. You mentioned about the amount of data that's going to be collected on a nightly basis. How are you going to crunch all that data?
Yeah, well, this is what lots of us are spending our time working out. So there's 2 sets of this. So one is the images that are taken night after night after night. And one of the things you do with those is stack them together. So we'll make a very deep image of the sky, and we'll release those once a year. So we'll gradually build up this amazing view of the sky, which will be fun. But the real challenge is in what's called transient astronomy, so things that change. And lots of people are worried about how to find their favorite object. Because if you want to find supernovae, for example, stars that explode at the end of their lives, you look for things that have got suddenly bright, and you can filter out lots of the other things. And clever people are working on that problem. My side of things is to try and make sure we can still be surprised. So we're trying to work out how we can find the interesting but unexpected things in that data. And that's a big challenge. And part of the answer is going to be asking people like all of you on this call to help us sort through things via what are called citizen science projects. So when we get going in a couple of years' time, keep an eye out for that.
Is that going to be a continuation of the Zooniverse?
That's right, yeah. So Zooniverse is plugged into the Vera Rubin Observatory, and we're excited by it.
Brilliant. We just got a question from Rosie here. Would it be more exciting if life could be found on Mars, to wonder why it's
on Earth? Yeah, it's a good question. So, if you've heard of SETI, which is the search for extraterrestrial intelligence, one of my friends, Rob Simpson, coined PETI, which is the plea for extraterrestrial intelligence, which is the feeling that we don't want to be alone in the universe. So I think it's really easy to frame this as wanting to find aliens. But you're right, of course, that either way, there's a scientific mystery. So if Mars had all the conditions for life and didn't form life, something that would be difficult to prove, but if life isn't common in the universe, then you have to say, why did it happen here? And you've got a couple of answers. So one is maybe there's something special about the Earth. Maybe the moon is special and in some way helps, or maybe having a Jupiter-sized planet in a Jupiter-like orbit keeps comets away and means life could be more stable. And there's all sorts of ideas like that. Or you say, look, it's just a lottery ticket, and we got lucky here and we didn't get lucky anywhere else. The precise combination of circumstances that lead to life are difficult. And I like to think of this as it used to be an astronomer's problem, right? The question was, are there enough places where the conditions for life exist? And we're close to answering that question. I think we could probably say yes at this point. So now it's a biologist's problem. What exactly do you need for life to get started, and what are the odds, and so on? It's a much harder problem. And if we solve those, then the absence of aliens becomes a sociology problem or a psychology problem, because then it's, why aren't they talking to us? Which is a much more difficult problem again. Yeah. But you're right, that the absence, and we've got to be careful that Mars is worth going to. I was told off once by Steve Squires, who led the teams that built the Mars rovers, Spirit and Opportunity. He told me off for being disappointed that Mars wasn't more like Earth, because he said, look, we go to Mars because it's not like Earth. That's why it's interesting. And I try and remind myself of that when I give these talks. So thank you for the prompt.
That's right. We've got another one here from Stephen Webber. He's asking, what are the chances of Martian samples coming back, given that the mission isn't near being built yet?
I think it'll happen. So as I tried to point out, there are a lot of steps left, right? So we've collected the thing we want to bring back, but there are 3 separate spacecraft that need to be built, several of which aren't designed and which do things that haven't been done before. We haven't had a rocket take off from Mars and go back into orbit. We haven't tried to rendezvous 2 spacecraft as far away from Earth as Mars. So there are immense technological challenges. It's always a good idea in space exploration to disbelieve anyone who's giving you a date. And so the target date for the samples getting back to Earth at the minute is the year 2031. And I will not be surprised at all if it takes another 10 years. In fact, I wrote a column for Sky at Night magazine this morning that explained that I won't be surprised by that. But I think just the idea that the samples are there and that we could go and get them will be a really powerful push that these robots will be built and we will go and do it and they will end up back on Earth, because it's just too tempting to have little bits of Mars sitting there waiting for us. And all we've got to do is go and pick them up. That's
brilliant. Well, thanks very much, Chris. David might have a question, but I think he's getting ready for bed with the looks at him. So thanks on my behalf. Thanks for attending the Argo Navis conference. It's been a fantastic end to the whole 2 days. And hopefully we can invite you back again to give us another talk.
Pleasure. As soon as we find anything else about the universe, I'll come and tell you about it.
Brilliant. David, you got a question?
No, it's been brilliant seeing you doing this live. Really, the word that stuck out is revelation, and yeah, we often look up at night and think, you know, what is happening up there? Somebody else doing something similar to us, and why is it possibly only us who won the lottery ticket?
Yeah,
Well,
indeed, it's a disturbing thought, but it's best contemplated out under a dark night sky, I think. So
Yeah.
do enjoy your dark skies.
Yeah, and I think the more people that get out at night, they'll start asking questions and getting far more interested in the detail of the dark skies above us. So thanks a lot for giving us a really good hour's worth there of astronomy and your insight and the facts and the research that you've given us. So you go to bed tonight knowing that you've done a really good job. And Alan, thanks for a great 2 days on the Argo Navis conference. It's been a pleasure being part of it. It's been it's drained me really. Look, I'm ready to go to bed. I just need to fill this now and I can go.
Well, thanks very much. And again, thanks very much, Chris. It really is appreciated. And thanks to the audience who stuck with us as well over the last 2 days. So
Yeah.
Thanks
And all
all.
the
See you soon.
questions.
night,
Well done.
everyone. Night, everyone.